We're going to be keeping on going with 3.11b. So we're going to be using differentials and linear approximations both to estimate the same thing. So just to remind you, differentials are the dy equals f prime of x times dx. And then linear approximations were like that tangent line stuff. So that was L of x equals f of a plus f prime of a times x minus a. So in our problem 1 over 4.002, let's start with the linear approximations stuff and go from there. So what we would need to do is think about a function that we could use to model 1 over 4.002. So the function that would be the best model for that would be f of x equals 1 over x. And then the number that would be the easiest for us to use in terms of being close to 4.002 would be 4. So f of x is 1 over x, which is also the same as x to the negative 1. We're going to need f of a in our model, or in our linearization. So f of 4 would be 1/4. And then we also need f prime of a. So we'll do f prime of x, which would be a power rule. So negative 1 times x to the negative 2, which would be 1 over x squared, negative 1 over x squared. So then f prime of 4 would be negative 1 over 16. So our linearization model is going to be L of x equals f prime of a, so f of a, so 1/4, plus f prime of a, so negative 1/16, times x minus a, so x minus 4. So L of x would be, I'm going to go ahead and simplify this and make it just a line instead of leaving it in this form. So I'll distribute that through. So negative 1/16 x, and then that would be plus 4/16, which is 1/4. So L of x would be, let's see, it's going to come out to be 1/4 plus 1/4, so 1/2 minus 1/16 x. So that's our linear approximation formula. If we wanted to approximate 1 over 4.002, then what we would do would be to take our model and plug in 4.002. So that would be 1/2 minus 1/16 times 4.002. And I'm not going to be a hero. I'm going to use a calculator for that. So we'll do 1/2 minus 1/16 times 4.002. That's going to give me approximately 0.249875. Okay, that's by linear approximation. Now we're going to do the same approximation using differentials. So using differentials, dy equals f prime of x times dx. Of course, our x value, we're going to use a convenient number, so we will choose 4 for our x value. And then dx is the amount of change from x. So the amount of change from 4 would be 0.002, and it's positive because it's larger than 4. And then we already know f prime of x. F prime of x, because we just did that over here, would be negative 1 over x squared. So in our differentials formula, dy is equal to negative 1 over x squared times dx, since f prime of x was that. Then the dy represents the change in y. The x represents our x value, and the dx represents the change in x. So this is going to tell me the amount of change in y when I'm using an x value of 4 and a change in x of 0.002. So dy will be negative 1 over 16, because remember my x value is 4, times dx, which was 0.002. So negative 1/16 times 0.002. 1/16 times 0.002. That is 0.000125. And it's negative. So dy is negative 0.000125. So what does this dy represent? Dy is the change in y. So you notice that this answer is nothing like the answer that we got from our approximation on this side. Well, that's because this is approximating the ending y value. This is approximating the change in y. So since dy is negative 0.000125, our new y value will be our original y value plus the change in y. So the new y is going to equal the old y plus the change in y. So when x is 4, our old y value based on our function, remember f of x was 1 over x, that was our model. So that would be 1 over 4 plus our change in y, which was negative 0.000125. That will be our new y approximate value. So 1/4 minus 0.000125 is 0.249875, which is the same thing that we got when we used the linearization. So to find, we should probably write that down. To find f of x plus dx, that's our new y value. F of x plus, whoa, I wanted to use a d, not a delta. To find f of x plus dx, that's our new y value. What we're going to do is take f of x, which is our old y value, plus dx, which is the, dy, which is the change in y. So our new y value is going to equal our old y value plus the change in y, which is what we set up here. So f of x plus dx, new y value, equals f of x, old y value, plus dy, which is the change in y. So now I want to look at what do x and delta x and dx and dy and delta y and y, like what are all of those things on a graph so that we can maybe understand what they are in terms of meanings. So I am going to start with this x value here. I need the right color. So no, that is not the right color. So here, I'm going from this little dot here and over. So this is going to be my starting value. I'm just going to call it x. And then this over here would, of course, be f of x because it's the height of my function at that x value. Now, this is my tangent line. And right at that point, x, f of x, the function and the tangent line have exactly the same value. But what I'm going to do is I'm going to scooch over a little bit from x. I'm going to scooch over quite a ways because I want you to really be able to see it. So I'm going to scooch over to here. And what we're going to call that distance here, that is the change in the x value. So what did we call the change in x when we did differentials? We called it dx. So this is dx, which is the change in x. So when I scooch over by dx, my new x value is x plus dx. Does that sound familiar? Because we were just talking about that over here, x plus dx. F of x plus dx is the new y value. X plus dx is the new x value. Yay. So x plus dx is my new x value. What's my new y value? We just talked about it. it is f of x plus dx. Now, what I see here is on my actual function, what's the difference in the y value between this ordered pair and this ordered pair? It's given by this little teeny tiny section here. So this little distance, I'm going to follow this over to here, I guess. This little distance here between the height of this dot and the height of this dot, this is dy. It's the actual change in y. Remember that dy is the change. That is delta y. Let's back up. Back that train up. That is delta y. Delta y. Delta y is the actual change. Dy goes with the derivative. Delta y is the actual change in the function. So when I move from x to x plus delta x, I have a change in height of my function. That change in height is delta y, which is the difference between f of x and f of x plus dx. Now, dy is the change in y using the tangent line approximation. So if I follow x plus dx up to my tangent line, up to here, this distance between where I started from and here where I'm ending, this distance here is dy. That's a really bad squiggly, dy. So delta y is the actual change from this ordered pair on the function to this ordered pair on the function. Dy is the change in y along the tangent line between those 2 points. So dy is a lot different in value than delta y. So dy is the change in y using the tangent line approximation. Dy, as we've talked about, dy is f prime of x times dx. Now, delta y is the difference between my second ordered pair and my first ordered pair. So my second ordered pair is f of x plus delta x, and my first ordered pair is f of x. Now, why did I put delta x here instead of dx? Well, dx is the amount of change in x along the tangent line. Delta x is the amount of change in x along the function. Well, it happens to be that those two things are the same. So delta x and dx are the same thing, but delta y is the actual change in the function's height, whereas dy is the change in the height of the tangent line when we go from ordered pair to ordered pair. I think I left excess space. So let's practice finding dy and delta y for this particular function when x is 1 and delta x is 0.5. So remember that dy is f prime of x times dx. Dx is the change in x. That's using the differential. And f prime of x is the derivative of the function at that x value. So using the differential, dy equals, we have to do f prime of x. So we're going to have to do the derivative of that. Let's do that off to over here. So if y is x to the 1/2, then let's just go with y prime would be 1/2 x to the negative 1/2. So y prime is 1 over 2 square roots of x. So dy would be f prime of x. So 1 over 2 square roots of, since we're using x equals 1, we'll put in 1, times dx. Now dx, remember, is the same thing as delta x. So this is also dx. dy and delta y are different, but dx and delta x are the same. So times
Samantha
dx,
Denyon, please come to the front office. Samantha Denyon, please come to the front office.
which is 0.5. So here we have dy is 1 over 2 times 1 over 2, basically. So dy would be 1/4. Now let's look at delta y. Delta y is the actual change in the function height. So we're evaluating the function at x plus delta x and subtracting the function at x. So to find delta y would be f of x plus delta x, so 1 plus 0.5, minus f of x, which was 1. So f of 1.5 minus f of 1. Since f of x is the square root of x, we would have the square root of 1.5 minus the square root of 1, which is basically the square root of 1.5 minus 1. So let's look at what that is approximately. I know dy as a decimal is 0.25. So let's figure out delta y would be the square root of 1.5 and then subtract 1. So that's approximately 0.2247 or 48714. Okay. So remember that delta y is the actual change in the function height when I move from x equals 1 over to x equals 1.5. dy is the change in the tangent line. If I draw a tangent line at x equals 1, then I move along the tangent line to 1.5. Let's see. I wonder how bad of a sketch I could do here, because my function is square root of x. So here, so if I draw a tangent line at x equals 1, a really bad sketch. So as I'm moving from x equals 1 to x equals 1.5, here is the point on my graph. So the difference in height here is delta y, which is 0.22, whereas on the tangent line, the difference in height is higher at 0.25. So from this level to this level would be the 0.22. From this level to this level would be the 0.25. So you can see that dy and delta y, this would be delta y, dy would be the tangent line approximation, are not the same thing, but they're close enough, in my opinion here, that's not that big of a difference.